Every day, the Earth receives visitors from outer space. Tons of space dust that mostly goes unnoticed. But sometimes larger objects can be seen streaking across the night sky. They are meteors. Only a few of these shooting stars survive the fiery descent through the atmosphere. For having withstood their ordeal, they are much reduced in size and given a new name: meteorites. Most of them are never found, but in 1954, one meteorite made its presence known in an extraordinary way. It happened in a small Alabama town where Ann Hodges was taking an afternoon nap on her couch when she was awakened by a sharp pain on her left side. A meteorite had crashed through the roof, striking her. It is the only verified account of a meteorite ever hitting a person. Of course, bigger rocks have fallen out of the sky. 50,000 years ago, a 50-yard-wide asteroid crashed into the ground and was vaporized in what is today the state of Arizona. All that was left was this 600-foot deep hole, the best preserved asteroid crater on Earth. And there's what happened to the dinosaurs 65 million years ago. That catastrophe not only wiped out the dinosaurs, but 3/4 of all of the then existing animal, marine, and plant species. Keeping track of asteroids and comets is a serious business, and it's an important aspect of the work the Jet Propulsion Laboratory performs as part of NASA's larger effort to protect our planet from cosmic marauders. As the saying goes, the dinosaurs didn't have a space agency.
Roger, on my mark. 3, 2, 1, mark.
Fortunately, we do. Join the hunt for space rocks. Asteroids and comets are as old as our solar system. They formed 4.5 billion years ago in the midst of a swirling disk of interstellar gas and dust. As the cloud contracted, our star, the Sun, ignited.
You can imagine when the solar system first formed, it started off as a giant cloud of gas and dust that starts to kind of coagulate under the influence of gravity. Gravity starts pulling everything together.
This is how the rocky planets, Mercury, Venus, Earth, and Mars, came to be. They endured unceasing bombardments from other objects as they carved out orbital paths around the Sun. One of those collisions between the Earth and a Mars-sized object gave us our Moon. Further out, the giant gas planets, Jupiter, Saturn, Uranus, and Neptune, came into being. But even here, there was likely mayhem. Uranus may have suffered an enormous collision, one explanation for why it is permanently tipped over on its side, the only planet in our solar system existing in such a state.
Most of the mass ends up in planets or the Sun, but there were little pieces left over. And eventually those pieces formed into what we know as asteroids and comets today.
While asteroids are leftover debris residing mostly between Mars and Jupiter, the vast majority of comets are to be found far beyond the orbit of Pluto. A region called the Kuiper Belt is believed to contain millions of them. And far more distant, surrounding the entire solar system, is a celestial sphere, the Oort cloud. Here, trillions of comets may reside. It's from these distant places that some comets find their way into our planetary neighborhood.
We now know that there's a sort of a cloud of icy, rocky bodies out there that are called long-period comets, or Oort cloud comets. These objects probably are remnants of the original gas cloud from which our solar system collapsed about 4.5 billion years ago, and they're still out there. Occasionally, they make their way into the inner part of the solar system, and they can come in, and then we see them as comets.
Compared to asteroids with their dark surfaces, comets are show-offs. For as a comet approaches the sun, dusty ices on its surface heat and light up, turning into a cloud of gas and dust, often having a trailing tail that can be millions of miles long. To the ancients, comets were viewed as harbingers of impending doom. But today, dread has been replaced by fascination. For these interlopers are relics, made up of the oldest and most pristine matter in our solar system. And it seems likely that we have to thank them for having brought to Earth long ago the elements that have allowed life to develop on our planet.
We know for certain that a pretty large asteroid or comet is responsible for the extinction of the dinosaurs. So from that standpoint, they can be incredibly destructive. Of course, we wouldn't be here without that. Maybe we'd be walking lizard people, I don't know. But it's certainly true that life today is very much a product of an asteroid impact, a destructive one. On the flip side, we think that there's a very powerful role that these objects have played in the potential for building life on this planet and perhaps elsewhere. If we just start from the very beginning, which is the seed of an asteroid or comet, that tiny grain becomes a site where molecules can meet and form more complicated molecules. So they become nucleation sites for chemistry to occur. So you can start with simpler things, even like 2 hydrogen atoms, but eventually those build longer and longer chains of molecules, some of which can be very complex. And eventually, all of those complex chemicals can migrate to a planet. So we think that there's a role that comets and asteroids have played over billions of years in seeding our planet with some of the chemistry that it may have needed to eventually evolve life.
The best known of all comets is Halley. It revisits the Earth about every 76 years. Its 1986 appearance was a highly anticipated event. This was the first time, given the dawn of the space age, that it was possible to venture out and meet Halley. And no one was more excited about that possibility than the then new director of NASA's Jet Propulsion Laboratory, Bruce Murray. Murray was intent on reinvigorating JPL, which he believed was becoming too cautious with missions he dismissed as being gray mice. He wanted, instead, for the lab to create daring new technologies used to explore destinations that would excite the public. These kinds of missions he labeled purple pigeons, for it would be impossible to ignore them. And for Murray, a mission to comet Halley, a once-in-a-lifetime event, was made to order. But any spacecraft sent out to meet Halley would have to overcome a major challenge.
Comets in general are in crazy orbits. Some are retrograde, some are highly inclined, so they are not easy targets to get to, especially if you want to get to them and pass them fairly slowly so that you can study them in detail. Halley's comet in particular was in a tough orbit to get to, and so there were various proposals on how to get into the right orbit.
Halley's retrograde orbit means that it circles the Sun in the opposite direction of Earth's orbit. A spacecraft flying by Halley would be like two cars speeding past one another, offering little time for exploration. Any attempt to rendezvous and fly alongside Halley posed even greater challenges. But a radically new idea surfaced, designing a spacecraft to be propelled by the pressure of sunlight, solar photons, similar to how wind pushes a sailboat.
So you need an enormous amount of energy to slow down when you get there, stop. You need a huge amount of fuel. And the idea of the solar sail is that you would need the fuel because you could use changing solar pressure on the sail to handle your acceleration and deceleration. That's what made it such a really interesting, fascinating, and also problematic technology because it's not something anyone had ever done before. It was really a science fiction idea. It was kind of way out there, and lots of other JPL people thought it was nuts.
Two different concepts were put forth to capture the power of the sun. The most audacious of the two was called a heliogyro, a structure resembling a dozen helicopter blades stacked atop one another, each 4 miles in length. They were to use the sun to spin up to 200 times a second. In comparison, the solar sail seemed almost conservative. Astronauts were to deploy from the space shuttle a razor-thin sail stretching a half-mile in length on all sides. Murray was so taken with the solar sail that he enlisted colleagues, including his friend, the popular scientist Carl Sagan, to help drum up support for a Halley mission. It was an effort that reached from the halls of Congress to Hollywood.
Now, what would this do?
Well, it takes you to where you want to go. So one mission that's being talked about is to rendezvous with Halley's comet in
I've always
1986.
wanted to do that.
Well, nobody's ever looked at a comet close up, and it lives mostly in the outermost part of the solar system. In fact, mostly lives between the stars. It's a piece of interstellar matter, and it'd be just fabulous to find out what it is. Also, this thing itself is, I think, tremendously exciting because, first of all, as it would be assembled in Earth orbit, it would be bright enough to see with the naked eye. Through a pair of binoculars, you could...
Solar sails and heliogyros were ideas far ahead of their time. But there was another purple pigeon whose development was further along. Solar electric propulsion, also known as ion propulsion.
Dr. Kenneth Atkins of the Jet Propulsion Laboratory described the advanced propulsion system.
Ion propulsion capability is 10 times as efficient as our conventional chemical rockets. And I think this is what gives us the capability to achieve a comet rendezvous.
When ion propulsion, like the solar sail, failed to gain traction, Murray next advocated a sample return mission, flying through the tail of Halley to capture some of its dust and bring it back to Earth to be retrieved by astronauts. It was another purple pigeon that never got off the ground, despite pleas from scientists.
For the first time in history, our children might be able to tell their children that they are the citizens of a nation which, for the first time, didn't simply and helplessly watch Halley fly by, but actually went out to meet it and to explore it.
In the end, it was the Soviet Union, Japan, and Europe that went forward with missions to meet the comet, what came to be known as Halley's Armada, a space fleet having no American presence, but one guided by two newly arrived scientists at JPL who were experts in tracking celestial bodies.
Our real role in the Comet Halley missions was, one, we had to predict where the comet was. That was my job. For the Soviets, for the Europeans, for the Japanese. And then we ran the International Halley Watch, which was a ground-based program to observe the comet in the infrared and the visible region to get astrometric data of where the comet was at any particular time.
Halley's Comet was kind of a training ground for myself, at least, for generating and writing software that could calculate some of the interesting questions that were being asked. In particular, questions like, how close is Halley's Comet coming to the Earth, and things like that.
In a face-saving gesture, NASA repurposed and gave a new name to a spacecraft near the end of its life and flew it past a comet. But there was no camera aboard, and it wasn't Halley's comet. Eventually, Halley receded from view, as did Bruce Murray. Frustrated by what he believed was a U.S. retreat from exploring the solar system, he stepped down as JPL's director 4 years before Halley's arrival.
Murray burned a lot of bridges with his campaigns for the purple pigeons and otherwise to save JPL. And at the time, well, then as now, NASA headquarters doesn't like it when centers kind of go off on their own to try to promote what they want to do and not what NASA headquarters has agreed with the White House should be done.
While none of Murray's purple pigeons took flight during his tenure, many of them would in years that followed. And looking back, perhaps what was more important for JPL than sending a spacecraft to Halley was the lab's pioneering work in predicting the path of the comet. For that accomplishment laid the foundation for JPL's future world leadership role in tracking near-Earth objects that could pose a threat to our planet and everything on it. Seven years after Halley's visit, 3 astronomers atop Palomar Mountain in California were searching the night sky for comets.
Could you please introduce yourself and tell me what you're doing there?
Yes, I'm Carolyn Shoemaker with a stereo microscope that was built specially to look at our films.
Okay, Mr. Shoemaker. What are we doing and what's going on tonight?
Well, what I'm doing here is laying out our game plan for tonight. We'll probably take about 50 films tonight.
Their luck had not been good. For months, they had experienced bad weather and cloudy skies.
It was snowing. It was just about the lowest point of all of our years at Palomar. Third straight month with virtually no observing.
During what seemed sure to be another disappointing night, the clouds briefly parted, and they rushed to the telescope and captured a puzzling image. It was an object near Jupiter, but it looked nothing like a comet. Was it, they wondered, just a reflection of Jupiter? Or perhaps some galaxy seen edge on? It turned out that the astronomers, Eugene and Carolyn Shoemaker and David Levy, had discovered a comet, and one like nothing ever seen before. Named after the 3 astronomers, Shoemaker-Levy 9 turned out to be a comet that 8 months before its discovery had broken into pieces due to Jupiter's gravitational influence.
And over the ensuing month, we learned that not only was this comet orbiting Jupiter, very unusual for a comet, but that it would impact Jupiter. And it wasn't just one impact, it was 21 impacts because the comet had broken up into the string of pearls. And so, real challenge, by the way, to calculate individual orbits for all those fragments. And I could confirm that with this software I had only recently developed. That was really the first real exercise of an impact probability calculation. It was for Jupiter.
This is a totally new event. The first time in the history of civilization, the history of the telescope, we are seeing an impact of a comet into a planet. Because of this, we are mounting the largest single campaign, the largest observing campaign for a single event in the history of astronomy. The good news is that it's going to do a spectacular demise into the atmosphere of Jupiter. The bad news is it's going to do it on the wrong side of Jupiter.
What Levy meant by the wrong side of Jupiter was that the fragments, which were estimated to range as much as a mile across, would be crashing into the backside of Jupiter as seen from Earth. And that meant that no telescope on Earth would be able to witness the actual impacts as they occurred. But on its way to Jupiter was JPL's Galileo spacecraft. By mere happenstance, Galileo would be in a position to witness the impacts live.
Galileo spacecraft was en route to Jupiter and that could look at the impact zone directly, whereas from Earth, all the impacts occurred on the backside and they rotated into view.
About an hour after each impact, the crash sites would be viewable from Earth, allowing ground telescopes to witness the aftermath. The excitement in the astronomy community about such an extraordinary event quickly began generating extra sensational press.
However, I was in the supermarket last Thursday, in the line, and I picked up a copy of The Sun. It's one of these tabloids that you slip underneath your six-pack of Coke on the way out. And anyway, it says, comet crash will start U.S. ice age. No government agency will verify the impending day of doom, but sources say that's only because they want to prevent wide-scale panic and rioting. This is a report by Mr. William Rock. I understand there's a few members of the press here today, and if Mr. William Rock is among them, I'd like a word with him after the talk, please.
But in the midst of Yeoman's witty remarks were actually some deadly serious implications.
The computer modelers are going nuts. There's a whole community of people within DoD who do nothing but model the effects of an impact, a nuclear detonation on Earth or an asteroidal impact on Earth. The problem is they don't have any data. So what they would dearly love, of course, is a 100 million megaton impact on Earth to refine their computer calculations. There are some obvious problems with that. And so the same computer modelers are adjusting their code for Jupiter.
I have another question down here. We only had about just over a year warning of this event. It raised an interesting question. What do you suppose is the minimum warning time we would have for any comparable event on the Earth?
That's something we have been thinking about. An asteroid that's likely to strike Earth is one that we probably already know about, and so if the orbit is well enough determined, we can simply integrate forward with the appropriate perturbations on the computer. The exception to that, of course, are the comets, the long period comets that can indeed come out of the sun, take us by surprise. But these apparitions of long period comets are far less frequent than the asteroids. But if a comet did come out of the sun, it would take us, it would pretty much take us by surprise, and there's not a great deal we could do about it, but that's a very low probability event.
Just as Chodos and Yeomans predicted, the first fragment of Shoemaker Levy 9 slammed into Jupiter's southern hemisphere on July 16, 1994.
Scientists didn't know what to expect because they were just little pinpoints with tails, and some were saying that these impacts would just kind of fizzle out, that we wouldn't even see anything. And then shortly after the predicted time for fragment A, we got a report that it was really there was a bright dot on the limb of Jupiter, so it was clearly visible, and we knew that fragment A was not one of the larger ones.
A massive fireball erupted, creating temperatures over 40,000 degrees Fahrenheit. The plume would rise nearly 2,000 miles above Jupiter's atmosphere. Over the next 6 days, at least 20 more fragments would slam into the giant planet.
As we went down the line, some of the bigger ones, when they impacted Jupiter, were releasing, by some accounts, millions of megatons of energy when they hit. Partly because they're coming in at high velocity, but also because these fragments were likely at least hundreds of meters in diameter each.
So in your mind's eye, sort of think of A as a 1 kilometer size object, maybe E is a 1.5, and then G, I suspect we're getting up to about 3 kilometers. What we're seeing is not deep in the atmosphere. While the projectile punches down deeply, all the hot stuff burps right back up to the surface. So these effects we're looking at
are up on top of the normal atmosphere. They're above the ammonia cloud tops. All these wonderful features that we're seeing here is something that's been brought up from depth that's now deposited on top.
And one of these collisions with the G fragment, which was the largest one, generated an energy of something like 6 million megatons of TNT explosive, which is 600 times the global nuclear arsenal.
If you were going to ask what's the size crater this would make on the Earth, if we're right about our estimate of the size and the energy, if it hit a continent, it would make a 60-kilometer diameter crater, thereabouts. Material that's blown out of that crater would essentially blanket the Earth with a layer of fine debris that would just block sunlight. It would just get dark all over the Earth.
It was not hard to imagine the repercussions of such an event aimed at the Earth. But there was not much of a response by NASA or the Defense Department to tackling the problem. That began to change 4 years later, after a prediction that an asteroid might hit the Earth in 2028 became front-page news.
That was a false prediction. And the scientist who made that prediction at the Minor Planet Center was basing it on really of approximations. We, on the other hand, could actually calculate the impact probability, and it was 0. No chance that this asteroid would hit the Earth. And so this became front-page news in the New York Times and many other newspapers. Here we had one prediction that an asteroid could hit the Earth, and another group, Don and myself, saying, no, it can't hit. And so there was massive confusion, and I think this was a wake-up call for NASA.
By the time of this media frenzy, NASA was responding to a U.S. congressional directive to discover 90% of all near-Earth objects large enough and potentially close enough to cause global extinction of life on our planet. Today, it's estimated there are almost 1,000 of these large objects. About 90% of them have been located. But there are many more smaller but dangerous near-Earth objects. So far, nearly 5,000 of them have been detected and designated as foes, short for potentially hazardous objects. Most of the hunting for asteroids is done by ground-based telescopes, but determining their sizes and potential for causing damage is hampered by the dim light given off by these dark objects. But an infrared space telescope, originally called WISE, has been helping to fill this information gap.
This was a mission to survey the entire sky in 4 infrared wavelengths of light. So wavelengths longer than what our human eyes can see. And the objectives of the mission were pretty simple, to just make this incredible all-sky map with a goal of seeing everything in these different wavelengths. Well, it also turned out that this project was quite unexpectedly good at sensing asteroids. As it turns out, WISE was spectacularly effective at not just observing these objects, but actually discovering new ones.
After WISE's onboard coolant needed for stargazing was depleted, it was renamed NEOWISE and repurposed as an asteroid hunter. For an infrared telescope can do something light-seeking telescopes cannot do: determine the size of an object.
This is because we're measuring the heat that comes off of the body. So rather than sunlight bouncing off the surface, we're actually seeing sunlight that is absorbed by the asteroid and then re-radiated as heat. So you can imagine that if we can measure the distance to the asteroid, and we know its brightness in these infrared wavelengths, we can actually figure out how big it is, because that sort of falls out of the equations.
But the Space Telescope's second life is nearing an end. Now in development is a successor mission.
Now we're working on the Near-Earth Object Surveyor mission. This is a new NASA mission whose objective is really to go out and map out the entire population of near-Earth objects as completely as possible. In particular, we're focusing on objects that are large enough to cause what I would call severe regional damage, meaning they're 100 or 200 meters across, and that's equivalent to something that's about a 200 megaton nuclear explosion. That's pretty bad. From my standpoint, this is a fascinating problem for a few reasons. One, just fundamentally, It's a natural disaster that we can prevent through fairly straightforward means. We can literally go look up, and if we do a thorough enough job of it, we have a chance of actually predicting whether or not there is something that's headed our way. And even if the answer is no, coast looks clear, that's a really good answer. It means it's something we don't have to worry about. So that just nice, neat solvability from my perspective is a really wonderful and rare thing in science.
Comets usually aren't shy about making themselves known. But asteroids with their darker colorations are far harder to spot. Early visuals of them were made by ground-based antennas that use radar to create ghostly images like these. The first ever close-up visit to an asteroid occurred a year before the Shoemaker-Levy 9 collisions, when the Galileo spacecraft was able to take a slight detour to capture some bonus science. A NASA mission having as its sole purpose the exploration of asteroids was achieved by the Applied Physics Laboratory in Maryland. Their spacecraft, named Near Shoemaker, flew by one asteroid and then went into orbit around a second one called Eros. This was the first time a spacecraft had ever orbited an asteroid. After spending a year observing Eros, the team decided on a daring ending to the mission: to attempt soft landing on the asteroid, something never before done, and something the spacecraft was not designed to do. Pulling off such a feat required radar science measurements provided by JPL's Deep Space Network and the expertise of JPL navigators.
Right now, we've just completed doing the last set of navigation solutions. It's the last optical navigation update, and we provide that solution in case we want to adjust very slightly the time of the next set of maneuvers. And the group that has done the orbit determination for NEAR, both radiometric using the Doppler radio tracking, as well as the optical navigation using landmarks on the surface of Eros, are done here at the Jet Propulsion Laboratory.
Okay, the cell data shows we're starting the maneuver.
Yeah, we're showing Doppler residuals are going down.
Okay. Yes, sir.
Okay.
We want this.
Yeah, we're 1.7 from the landing site, Dave.
Yeah, well, let's see now
that's slant range.
Get the maneuver started.
As navigators and as mission designers, this is the kind of challenge that we want. It's a very new, exciting, and challenging kind of mission to rendezvous with an asteroid and to attempt to touch it on the surface as lightly as we can. And I think we're certainly excited to find out what happens and how gently we can put it down.
In about 50 meters per second, or 50 meters low is what Gene says.
Those pictures are really spectacular. Yeah, you guys can celebrate now.
They're already popping the champagne corks. Hey, it looks like we hit less than 2 meters per second, and it did survive enough to track on the surface now.
We have two-way lock.
We have two-way lock.
After surviving the landing, the spacecraft continued operating for another 2 weeks, an impressive ending to an already successful mission. The first spacecraft to fly by an asteroid and a comet was a JPL mission whose purpose was not to chase down near-Earth objects, but to test a dozen advanced but risky technologies that larger, more expensive missions were hesitant to use. This was an effort to show that future projects could be smaller, less expensive, and capable of flying at times autonomously. At the top of the list of innovations was ion propulsion, a technology pioneered by NASA's Glenn Research Center that years before had been proposed for a mission to Halley's comet.
Ion propulsion is designed to give fast and flexible access to the solar system for missions of the future. The first time I heard about it was from a Star Trek episode. It was an episode called Spock's Brain, for those of you who are Trekkies. And to me, one of the neat things about working on a project like this is we're really getting to turn this fantasy into reality, and that's very exciting.
Mark Raymond, a self-professed space nerd, decided as a young child that he wanted to be a rocket scientist. And now he was living his dream, having been handed the reins to Deep Space One, a spacecraft that really did sound like science fiction. Ion thrusters make use of atoms of xenon gas, which are given an electric jolt. That disturbance results in an electric charge, and the ions shoot out of the engine at tremendously high speeds, upwards to 90,000 miles per hour. But because all of this is occurring on atomic scales, the thrust is incredibly gentle and slow. Going from 0 to 60 miles an hour will take Deep Space One 4 days.
The thrust from our thruster is comparable to what I feel from the weight of this single piece of paper in my hand. That's how hard the ion propulsion system pushes on the spacecraft. But with time, the thrust builds up, and ultimately we can achieve very, very high velocities. It's what I like to call acceleration with patience. The spacecraft is also smart enough to know how hard the sun and planets are pulling on it, and it can actually determine where it's going. An analogy I like to give for how powerful the combination of autonomous navigation with ion propulsion is, compared to what we can do today, these two technologies are like having your car find its own way from Washington, D.C. to Los Angeles, arrive at a designated parking space, and do it all while getting 300 miles per gallon.
7, 6, green board. 5.
Of course, Deep Space One first had to get off the ground.
Main engine start and liftoff.
That called for a rocket having a conventional propulsion system.
From the Delta rocket with Deep Space One, testing the spacecraft technologies of the next century.
Within minutes of the launch, Deep Space One's high-risk billing seemed already in play.
When we launch a spacecraft, we calculate where it will be in the sky and what time it will turn on its radio transmitter.
They're still running the receivers attempting to acquire. BSN is green at this time.
And the signal didn't show up. That's not where you want to run into problems on the mission.
Flight 8. Go ahead. I just reported again, they still do not see a downwind signal. I copy that. Thank you very much. We're going to head and proceed with our contingency plans here. Stand by. Copy.
There were a lot more issues on that spacecraft than other spacecraft I've flown since.
Go ahead. I just reported again, they still do not see a downwind signal.
A lot of things go into that because we're kind of pushing the boundaries. We're building these things for the first time.
Also be advised that the station is currently experiencing some receiver problems and they do not see a signal. I copy. Thank you.
This moment of flight jitters eventually passes when the spacecraft reports that it is alive and well. The team spends the next 2 weeks preparing for turning on the spacecraft's ion propulsion system for the first time.
This was the big day when we were actually going to light it, go to warp power, emit that cool blue beam, and get underway with our powered flight.
At 18:59:00. Ace, this is flight. You are go for radiation of India Charlie 018, X-ray 01 at 18:59.
This is the moment that is hoped will change the future of deep space exploration.
Right, once the accelerator shifts down some, real high frequency stuff does really awesome.
It'd be interesting to see if the doc, see stuff in the doc first.
Almost bet on. That's right. Seconds. This will change to true. Then we'll go through the startup sequence.
Unit 1 team, this is the mission director.
Prepare for warp speed. Yeah, right.
So we had all these people here. We sent the commands to the spacecraft, and sure enough, right on schedule, the spacecraft went through its own final procedures to start the engine, started the engine. It worked great.
There it goes.
There it goes. All right.
Congratulations, Jack. Everybody. Congratulations. Not me. You guys.
Hey, Jay.
We lit off.
Current you're looking at is right there. 0.5. There it is.
Everybody in mission control was all excited. People in the hallway were all excited.
Well, we're in standby. We had 20 recycles.
We're seeing TDC mode.
Well, the spacecraft had thrust for 4.5 minutes and then stopped. And so we immediately started trying to diagnose the problem.
I think we need to focus on this. Roger that. Please consider your evaluation for restart.
People, excess people filter themselves out of the room. A lot of noise, a lot of crowding.
After regrouping, the team tries restarting the engine.
Thank you, flight. This is Mission Director. You're authorized to radiate. Command DSN file Uniform Charlie 065 Alpha 01.
All units be advised, the thruster is off again.
Time limit, and we shut down and we're now in standby.
Roger that. Is there an evaluation of what caused the sequence of events?
There's discussion going on right now about that. We'll get back to you.
So every time it arcs, the high voltage cuts off and then goes back on automatically.
Right, to try to clear the fault. That's right. That's good for
A number of attempts are made, all with the same result.
Shut down.
Did it happen right away as time goes?
Each time that happened, our spirits went down a little more. Ion propulsion was the primary objective, and here we were unable to get more than 4.5 minutes of thrust. And in fact, our minimum success criterion for Deep Space One was to thrust with the ion propulsion system for 200 hours. Well, we still had another 199 hours, 55 minutes, and 30 seconds to go.
While disappointing, these kinds of shutdowns didn't come as a total surprise. Similar events have occurred during lab tests.
Plasma wave is we're going to get the search coils coming out and see how they correspond. If I were arc and you were burning for a while, it's probably a noisy burn right there. Because it should clean up to be fairly clean once the accelerator works right.
There may have been just a small piece of contamination in the thruster, in the ion engine, left over perhaps from launch when the whole spacecraft was shaken violently.
Can we set up the times relative to what we're seeing?
We did a number of things, including turning the spacecraft so the engine would point toward the sun and away from the sun. That would loosen this particle so it could just drift away.
After 2 weeks of using the sun to alternatively heat up and cool down the spacecraft, the propulsion system was tried again. The era of ion propulsion had arrived.
Over the course of the mission, we put it through its paces, we tested it thoroughly, we showed we could count on it to propel the spacecraft, we could navigate with it. It was wonderful. That meant that many subsequent missions that would have been impossible without ion propulsion then were possible.
What followed was a whirlwind of testing the other technologies on board. And only 9 months after launch, with almost all of the mission's objectives met, the team was eager to fly by an asteroid named Braille.
That was a great way to take all these new technologies and show that you could do planetary science.
You have to say it in French.
We're out there, let's go use all this fancy stuff to go take pictures of something.
The asteroid Braille was co-discovered just 6 years earlier. One of the two co-discoverers was Eleanor Glow Helen, a JPLer and a pioneer in asteroid hunting. That the asteroid was found was an impressive feat, for the asteroid was so dim that Deep Space One was almost unable to spot it. And just hours before the encounter, a software bug caused the spacecraft's computer system to overload, requiring a reboot.
The fact that the spacecraft was very temperamental, like, almost made us not able to do that encounter. We went into safe mode the morning we were supposed to do this flyby. I got a text message. Back then, you know, we didn't have cell phones. We just had these pagers, but the pagers were fancy ones that you could get a text message on. I got this text message that said, we're in safe mode, and I'm like, wait, the encounter is tonight. It takes 3 days to recover from safe mode. Oh my gosh, I better get into work.
We sampled about every...
Racing against the clock, the team beamed up new instructions. The last command was transmitted with only minutes to spare. The science results were modest. The few images of the asteroid were taken at a further distance than intended, causing them to appear out of focus. Still, this had been the smallest celestial body ever targeted by a spacecraft, coming within 17 miles. An impressive accomplishment that convinced NASA that the mission was worthy of a second shot. The next target would be a comet. But in November 1999 came the most serious crisis of the entire mission. The spacecraft's star tracker, which looks at stars to determine the spacecraft's orientation, ceased working. Without it, the spacecraft was left in a state of confusion, knowing neither up from down nor right from left.
The star tracker on Deep Space One is responsible for telling the spacecraft how it's oriented in the zero gravity of space. We know where it is and where it's going, but we can't tell where it's pointed without the star tracker.
The spacecraft, for all intents and purposes, could accomplish nothing of value without the star tracker. There was no reasonable, rational prospect of being able to continue the mission. But I didn't want to give up that easily.
Normalize all these to one number and decide what to add or subtract.
The team started working on ways that we could rescue this spacecraft from across the solar system. With a fatal, catastrophic failure for which there was not even a concept for how we might recover. All we had to work with was what was on board the spacecraft, plus, of course, ones and zeros that we could send to it. There followed months of very, very long hours, every day, constant stress, this feeling of, you know, I want to get this spacecraft working again.
There ended up being only one possible fix: to send up new software that would reconfigure the spacecraft's camera to do double duty as a star tracker and a camera.
The science camera was not designed to do that and had a much narrower field of view. The star tracker has a giant wide field of view that can see a significant part of the sky. The science camera is sort of like trying to drive your car looking through a soda straw. Basically, what we needed to do from then on was pick a direction that we wanted to thrust, find a star near there, and then thrust at that star for a while, And then after a while, the navigators would tell us, now we need you to point the thrust in this other direction. Like, oh, okay, let's go find a star over there that we can thrust at.
Like a sailboat tacking with the wind, Deep Space One zigzagged its way to a comet named Borrelli. The closest approach would be on September 22, 2001. 11 days before then was 9/11, the day the United States was attacked by 4 hijacked planes.
It just turned the world upside down. Personal emotions about it was, by gosh, we are going to accomplish this thing. We aren't going to let this stop us. The lab is completely empty. There's guards everywhere with guns, there's guards with shotguns at the front gate. And, we have special permission to be the only people allowed on lab because we have this operations work to do. It was very emotional. Said a lot of people had their American flags. I'm a volunteer for the JPL search and rescue team. I had some inkling of what was going on in New York, so I wore my search and rescue helmet that day.
We had faced so many difficulties. We'd had to make so many decisions. And, Deep Space One had not been designed or built to encounter a comet. And the encounter at Borrelli didn't go the way we expected. Instead, it was perfect. Years of nursing along this damaged, wounded spacecraft, it was pretty rewarding.
Scientists were elated with what were then the highest resolution pictures ever taken of a comet. The stubborn team of engineers could also take pride in having opened up a new chapter in robotic space exploration. Three months later, with the spacecraft running low on fuel and no other science destination within reach, the mission was officially declared over. Today, Deep Space One, a small spacecraft operated by a small team with big hearts, silently circles the sun.
Perfect, okay. See ya! We're not?
It is nice up here.
Correct. Copy. You're clear to ground.
Okay. Here we go.
During the same year that Deep Space One flew by asteroid Braille, NASA's first mission devoted exclusively to comet exploration was underway. The vehicle wasn't a balloon, although this one was part of a critical pre-launch test. The main goal of this mission, called Stardust, is to send a spacecraft out to capture samples from a comet and then bring them back to Earth. What's been pushed out of the balloon is a model of the capsule that is to contain the comet particles. This drop test is to determine how hard a landing the capsule can withstand. The landing area is the Dugway Proving Grounds, a remote military facility in northwestern Utah. The winter weather makes for a cold outing, but the wet ground will hopefully make for a soft landing.
It wasn't traversing. They landed right on the road.
All right.
A comet sample return mission was first proposed for Comet Halley. The scientist involved in that original proposal, Don Brownlee, had never let go of the idea. And the comet that's been chosen to sample, Wild 2, has an unusual history, as comets go.
We have this wonderful situation. The comet came from the edge of the solar system, came into the inner part of the solar system where we are, and then we sent a spacecraft out halfway to Jupiter to meet this thing. So it's really kind of a sort of a magical situation, I think.
Wild 2 is believed to be as old as our solar system, and it is thought to contain some of the most pristine and pure materials out of which the solar system was formed. That made for a convincing case to greenlight the mission. And the price tag didn't hurt its selection chances either. This was one of NASA's early faster, better, cheaper missions. The goal was to fly a spacecraft for less money and on a faster schedule. And Stardust promised just that. The spacecraft is a straightforward design having few bells and whistles. It is to be powered by solar panels, but no spacecraft has ever been asked to travel as far from the sun using solar energy as this mission will have to go. And no spacecraft had ever flown as close to a comet as was planned for Stardust, which is why the spacecraft is front-loaded with bulletproof shielding.
We're playing a game here. We want to go close as possible to the comet to get the best images and to collect the most amount of sample, but we don't want to get hit by large enough particles to destroy the spacecraft.
Stardust's most unusual feature is its comet dust collector. It resembles a tennis racket full of ice cubes. But this blue material is an ultralight compound called aerogel. Sometimes referred to as frozen smoke, it's a solid that is 99% air. JPL researcher Peter Sue made a career out of finding ways to use this strange material.
Aerogel, although it's very fragile, but it has very high compressive strength. And let me demonstrate to you, this piece of aerogel weighs about 10 grams. This piece of plexiglass is about 50 grams. That's already 5 times the weight. This is 1,000 grams. This is another 1,000 grams. It's 2 kilograms. So this is 2,000 times its own weight.
While aerogel can carry more than its own weight, it is also porous enough to capture intact comet particles that are moving faster than a bullet. A year after its launch in 1999, Stardust gathered in the first 2 samples of interstellar dust. Then it was on to a full dress rehearsal of a comet encounter by flying by Asteroid and Frank. To protect the spacecraft, Stardust was kept at a safe distance of over 2,000 miles. Still, engineers were delighted with the test. And scientists even got a far-off peek at the asteroid. Another year passes before the encounter with Wild 2. And as the day nears, the comet isn't cooperating. It's dimmer than expected. And that likely means there will be far fewer dust particles to collect than wanted.
As far as the brightness of the object, the photometry is concerned, we're somewhere between 5/7 and 5/10 the amount of dust that we expected to observe. Yeah, there's less light coming from the thing this time, less flux.
The only way to collect more dust is to fly closer to the comet. But flying closer increases the risk that the mission could be lost.
Now, originally, these observations we weren't going to use to change our plans. We were just going to use to confirm that we're still in the ballpark.
This meeting offers a rare look into how such pressure decisions are made in real time. The encounter is only 3 days away. At the table are JPL engineers, navigators, scientists, a NASA headquarters representative, and by phone, the spacecraft contractor Lockheed Martin. Given the concern that debris shedding off the comet might ruin the encounter or even destroy the spacecraft, the question on the table is how close should the flyby be?
I didn't make too much noise about going to 300 at the time because there is a chance that we might lose all of the images if we go into 150.
If we do go into 150, pretty much are close to collecting the particles, but if we go into that close, there's about a 4 times higher chance we will lose the image sequence during the flyby. So what's science assessment?
Well, my recommendation is we target for 250, which is a modest correction. This is better than sticking at our target value of 300 kilometers we did in the past. I'll use Sham's golf analogy. We're approaching the hole, and we're doing tweaks as we're coming in.
And there's still a probability it'll work. I mean, it's not saying that it won't work. It's just
what do you mean?
Yeah, but
what do you mean probability?
Well, I don't know. I mean, I'm not saying it's an absolute failure. I'm not saying it's an absolute success.
You know, if we're opening up, we're exposing ourselves to some new risk we haven't imagined, then that's really a stupid thing we'll always be crucified for. And if we lose imaging close in, we take a gamble. We've always known that the comet could disintegrate at any minute. It could turn off. It could turn on. It's an uncontrolled beast.
Okay, I think another data point is independent of science. I will not support a 150 kilometer flyby. I will be dead set against it.
So your recommendation is 250?
250.
After all this back and forth, the team is in accord. The trajectory will be changed to bring Stardust 50 kilometers closer to the comet. If Wild 2 has any more last-minute surprises, there are preloaded contingency plans aboard Stardust that hopefully will allow the spacecraft to respond on its own.
Hey, Tom, you're really fading out. You've been breaking up now.
Yeah, we got a lot of static here.
Good morning. This is Stardust Mission Control at NASA's Jet Propulsion Laboratory in Pasadena, California.
It is now 1 day after New Year's Day 2004. The time for the comet flyby has arrived.
After nearly 5 years and 2 billion miles of space travel, Stardust is about to perform a flyby of comet Wild 2.
It is also just 1 day before the landing of JPL's Opportunity rover on Mars. A busier time would be hard to imagine.
CNEOS station started systems. This is closest approach at this time.
We are going into an unknown environment. No spacecraft has ever gone this close to a comet.
Is that consistent with the 4-degree roll, which we expected to see?
The moment of closest approach passes. Stardust is still sending back a signal. It has survived the encounter.
Life is tremendously good. We've flown through the worst of it, and we're still in contact with our spacecraft.
Soon the spacecraft will be transmitting back news that it has captured thousands of particles, and to the delight of everyone, images of the comet.
You've seen these pictures? That's fantastic.
Yeah.
Nothing else in the universe looks like this, you know?
That's right.
Thank you. Nothing.
Looks a lot different than Halley. It looks a lot different than Borelli.
We were expecting some kind of rubble pile looking thing, just a dark black object, broken charcoal briquettes or something. It's just kind of a smooth, boring thing. We were completely wrong.
Wilt 2 was a far stranger object than imagined. The comet's surface was dotted with towering pinnacles, steep cliffs, and oddly shaped craters.
It was absolutely astounding. The first picture we got back showed these tremendous features, which we now call left foot and right foot, which looked like someone in a big clown suit just put their left foot and right foot into the surface of the comet. Yet these are kilometer-sized features that are hundreds of meters deep.
The flyby, though, had been far more dangerous than expected. Dozens of jets had bombarded the spacecraft at a rate of 1 million particles per second. Like a geyser erupting, jets are outbursts of material from a comet caused by heating by the sun.
We fly these missions and we do the best job possible to model everything we think will happen. The closer you get, the more dust you get. Maybe there's a few big jets that are waiting for us, gunning for us. And our prediction was no. And we were proved wrong, quite wrong, but we did survive.
With its bounty of comet and interstellar particles safely on board, Stardust, sandblasted but still sturdy, began its 2-year journey back home. Once near the Earth, Stardust is to release its capsule, which will have to endure the intense heat of re-entry through the atmosphere. Next, a parachute is to deploy, which should provide the capsule with a soft landing in Utah. Helicopters are to retrieve the capsule. Then this cosmic cargo is to make its way to a lab at the Johnson Space Center in Houston for detailed examination. That's the plan. But a parachute had failed to open on another JPL mission called Genesis. Its capsule, containing samples of the solar wind, slammed into the Utah desert. Fortunately, enough particles survived the hard landing to be useful for scientists. But no one wants to see a repeat of such a shattering experience. After a journey of 7 years and nearly 3 billion miles, the capsule re-entered the atmosphere at a speed of nearly 29,000 miles per hour, the fastest re-entry of any human-made object on record. Witnessing the spectacular entry were scientists flying aboard a NASA Ames research plane.
17 degrees aft.
The blazing capsule, filled with comet particles, now looked to be itself a comet.
Okay, we have confirmation of a main chute.
All stations, main chute is open. We're coming down slowly.
Stardust was the first sample return mission since Apollo astronauts brought rocks from the moon back to Earth. Inside the capsule were thousands of samples of comet and stardust that were shared with scientists worldwide. These particles, the only known samples from the outer solar system, were once part of a primitive, ice-rich body that formed well beyond Pluto. But surprisingly, many of the rock dust particles were similar to those found in primitive meteorites that formed close to the Sun. Apparently, these particles were transported to the distant comet-forming area in the outer regions of our solar system. Another discovery was the presence of the amino acid glycine, a fundamental building block of life. Its detection has added credence to the idea that the materials necessary for life to arise may be spread in abundance across the universe. While Stardust brought back samples from a comet's surface, JPL's Deep Impact mission was designed to hit a comet in hopes of revealing what materials reside in its interior.
5, 4, 3, 2, 1. We have ignition and liftoff of a Delta II rocket carrying Deep Impact, NASA's journey to unlock the mystery of the solar system's origin.
And the air starts have ignited.
Being launched into space are actually two spacecraft, the Deep Impact mothership and its cargo, a small washing machine-sized impactor to be released to collide with a comet. The two spacecraft were built by Ball Aerospace, with JPL responsible for management oversight and creating the especially complex software required for the mission.
We had 12 months to complete the assembly of the prime spacecraft, complete the assembly of the impactor spacecraft, go through the entire environmental test program, fix the flight software, fix the fall protection, fix all the bugs that we found along the way, and figure out in parallel how to hit the comet.
Hitting a comet was something no spacecraft had ever done. And to have any chance required creating computer simulations at JPL. As often as not, the early simulations resulted in misses. And then, 2 months before launch, a near catastrophic mistake was made.
There was that black day in November where somebody came in and accidentally deleted all the files. Sequences that we were working on for post-launch, encounter, everything, gone on one night. Deleted because somebody thought they needed space on a server. And it was like, how in the hell do we ever recover from this?
The solution was to work intensely long hours, and the pressure didn't let up post-launch. The journey to the comet, named Temple 1, was a short one, just 6 months. When only halfway there, the comet was already in sight. The JPL flight team barely had enough time to settle in before the encounter was upon them.
Normally it takes many months to launch a spacecraft and check it all out in flight and learn its idiosyncrasies and get it all calibrated and working good. And so to launch the spacecraft and only 6 months from then have an encounter was very challenging. We were sleeping in our offices level of working hard. And I came in one day, to my office, and I had my bedding all set up, and somebody had turned down my sleeping bag and put a mint on my pillow and left a little note that said, "Complimentary turn down service." It was, it was crazy, crazy days.
And what Deep Impact was expected to do sounded a little crazy too. What's been described as hitting a bullet with a bullet. After the impactor is released, its onboard navigation system has to visually find the comet in order to execute 3 targeting maneuvers. 3 chances of zeroing in on the comet.
The impactor, once we release it, has an auto-nav system like we introduced with Deep Space One, and it locks onto the comet and tries to make sure that it's going to hit it. And it makes that first correction based on information from a long ways away. And so each successive correction as we get closer is going to be better and smarter. And so there wasn't a lot of actual commanding going on. It was mostly we're watching the spacecraft to make sure nothing funny happens.
All of this is to occur on the 4th of July. But Comet Tempel 1, not to be outdone, has already been shooting off its own celestial fireworks. Comets are known to sometimes have sudden outbursts, releasing massive amounts of gas, ice, and dust that briefly increase their brightness. A concern is that if Tempel 1 decides to flare up during the encounter, the impactor's auto-navigation system could become confused. Worst case, the impactor might miss the comet entirely. It's not what the team wants to happen on a national holiday.
Mission, impactor flight, all impactor spacecraft subsystems green at this time.
It is now the 4th of July. The time of impact is 90 minutes away.
We are turning to the burn attitude. Target ID 6.
Copy, thank you.
The first impactor trajectory maneuver, or ITM, is underway.
Impactor flight, impactor prop.
Flight prop.
LEC TCM thruster firing with accumulated on times increasing.
Copy, thank you. Flight confirms your go to radiate.
Roger, on my mark. 3, 2, 1, mark.
Cat bed temps look as expected. The accumulated on time is about right as well. And we'll give you a more full report later.
Copy, thank you.
The comet is not yet done with its surprises.
What's the most difficult issue that's confronting the team right now then?
Right now it's the comet, which is why we're going there. It's presenting a very strange shape to us. We've been watching it all day as we get closer. We initially thought that this thing was something like a pickle. As we're getting closer, it looks like it's more like a banana. And the latest resolution that we have in the rotation that it's going is that we're looking at the end of it, and the end of it is basically triangular. So it all depends on what that comet does and what type of face it presents to us, and we have to solve for that, so that's the challenge.
And it appears that this has been quite a temperamental comet. Over the last couple of days, we've seen several outbursts from it.
Yes, that's true. We have seen the actual jet outbursts that brighten it, so it's very exciting for the scientists.
And nerve-wracking for the engineers. And even worse, the results of the first impactor maneuver were not what was expected.
It was the biggest movement off the comet we have seen, period. Even more than any of the simulations.
And that knowledge raises the possibility that deep impact might miss the comet entirely.
And the chatter is starting up that everybody's really worried on whether we can correct for that and come back in again.
Flyby flight, flyby autonav.
Go ahead.
The autonav flyby B-plane is 365.8 by 341.0 with a time of flight correction of less than 1 second at this point. Flyby flight, flyby autonav.
Go ahead.
I'd like to add to that B-plane information by saying we're about 1 kilometer off from the ground nav solution.
I was an extra set of hands, so I was basically moving around when issues would come up. As it turned out, that first correction kind of took us off in the weeds a little bit. They're aware of it and worried about it, but they're also like, it's supposed to bring us back. It was hair-raising.
After ITM-2, we have 6.5 kilograms of fuel remaining, which equates to 31 meters per second.
Fly-by thermal. Request to go offline for 2 minutes.
Dan, sitting next to me, he looks like a ghost because all the blood just drains out of him. And he says, Care, I need to go off net for a few minutes. You know, he goes off net, then he comes back 5 minutes later, and he looks better. And, you know, he kind of leans over to me and whispers to me saying, I just threw up. Because he was so sick from how big the ITM was, and he wasn't sure whether we'd come back in again or not. We can't do anything about it. All we can do is trust the work that we did.
We've seen the comet in all three cameras. We've seen it in the impacting camera, the two cameras on board the flyby spacecraft as well.
Providing live commentary during the event is Don Yeomans. Yeomans is blissfully unaware of the concerns over trajectory maneuvers, but he has his own reasons for being anxious.
They needed some stooge to get out there and talk to the media. Either it was a smashing success or a horrendous failure. And so I was just worried sick that I would get this question after the fact that, Dr. Yeomans, NASA has spent $240 million on this deep impact mission, and you guys missed?
So this is our best image to date. It's only going to get better, much, much better. Now it looks bright, but it's actually a very jet black object that is being overexposed to show the light. It's sort of rotating around an axis that is more or less up and down. And so you're looking at the small end of the pickle here. It's a 9-mile pickle, mind you.
Impact flight, we've begun ITM-3.
Impactor flight, impactor prop. We also see TCM firing for ITM-3.
Copy.
The last of the 3 thruster burns is underway. Nothing more can be done.
Mission, this is flyby Pulpitech.
Go.
Reporting on our last enabled state change for flyby, final imaging before shield mode. We have a disable of all ADCS performance. Basically, we're left with what keeps the hardware talking. ADCS, you're on your own.
Copy.
There are some of the images coming down from the spacecraft.
Oh, my, look at that. Looks like we've got...
No longer a pickle, more of an eggplant.
Yeah, now we're moving from the pickle to the eggplant here, and it looks like we have some clear surface features over there on the right. A dark depression, perhaps?
Look at the jets. Look at all the jets. Yes.
I have a little voice in my ear that tells me that we can put up the impact camera image in our monitor right now.
Okay. This is the impactor image, the spot where we're headed for impact. And the spacecraft's doing remarkably well for something that's about to vaporize. It's getting closer. We may be getting some serious dust hits. Our brave little spacecraft is in a very hostile environment here. We're going not only faster than a speeding bullet, we're going about 10 times faster than a speeding bullet. And that puts Superman to shame. We're expecting to lose the spacecraft any minute here. But it's doing one heck of a job just before checking out.
Flight, this is Telecon. We have lost the block.
Copy that.
The mothership, flying underneath the comet, recorded the aftermath. The impact was far more dramatic than expected, generating a brilliant flash of light and an immense fluffy cloud of ice, dust, and gas. That the comet's surface was so extremely fine, weaker than powdered snow, was a major surprise. This was no ice cube comet.
A crater and ejecta that's just enormous. It's considerably brighter and considerably more material coming off than I thought.
Also unexpected was the sizable amount of organic material that was detected. Yet another indication that comets and asteroids may have seeded the early Earth with the building blocks of life.
We've got all the data we could possibly ask for it, and the science team is ecstatic. And not a one of them can believe they're being paid to have this much fun.
Two, 3 o'clock, 4 o'clock, rock. 5, 6, 7 o'clock, 8 o'clock, rock. 9, 10, 11 o'clock, 12 o'clock, rock. We're gonna rock around the clock tonight.
There was more fun the very next day. The Comets, the original backup band for Bill Halley and the Comets, were on a nostalgic tour and made a surprise visit to JPL to offer their musical congratulations. Word of their presence quickly spread, and soon a spontaneous celebration erupted. These comets were rocking before there was even such a thing as a space age. And they still knew how to make an impressive impact of their own. Years before, after Voyager's final planetary encounter, the legendary Chuck Berry had played on this same spot. Now JPLers could also boast of having rocked away to the sounds of rock and roll's very first band.
We love you all.
Deep Impact's impactor was no more. But the mothership had survived, and the team was eager to sign up for another mission. 5 years after the Temple 1 encounter, Deep Impact flew by a second comet, Hartley 2. JPL's Stardust mission was also repurposed. It revisited Temple 1 to see the aftermath of Deep Impact's collision with the comet. And Deep Impact was followed up by NASA's Goddard DART mission. The spacecraft flew into a tiny moon orbiting an asteroid to demonstrate how they might be moved slightly off course. Keeping track of asteroids and comets is an international effort. A Chinese lunar orbiter flew out and passed by an asteroid. The European Space Agency's Rosetta mission, with a JPL science instrument on board, accomplished the first mission to deploy a lander to a comet's surface. And NASA's New Horizons mission holds bragging rights to the most distant object ever explored, following its flyby of Pluto. After JPL's innovative sample return missions, Japan's space agency has gone a step further. Their Hayabusa 1 mission landed on an asteroid, collected tiny grains of material, and brought them back to Earth. The Japanese repeated this remarkable achievement a second time, a decade later. NASA's OSIRIS-REx mission has also collected samples from an asteroid, which are now on their way home, scheduled to arrive in 2023. The technology advances from JPL's Deep Space One mission were put to use on the laboratory's Dawn mission. Using ion propulsion, Dawn was able to orbit 2 worlds in our solar system for the very first time: Vesta and Ceres, the largest objects in the asteroid belt. Recently launched is NASA's Lucy mission, that is to visit asteroids that share the orbit of Jupiter. And Psyche, a spacecraft managed by JPL, will soon be on its way to an asteroid made not of rock or ice, but metal. Flying a spacecraft propelled by a solar sail finally succeeded in 2019 with the Planetary Society's tiny LightSail 2 spacecraft. This publicly funded mission stayed in Earth orbit for 3 years before re-entering the atmosphere. A more recent NASA solar sail mission failed to deploy. All of these missions are about learning more about asteroids and comets, so that we might better defend against them. One element of planetary defense is called mitigation. What might be done should a near-Earth object threaten our planet.
There are lots of mitigation ideas. Putting a solar sail on the asteroid, throwing rocks off the surface. There's gravity tractors. Just using the gravitational attraction between the asteroid and the spacecraft and thrusting on the spacecraft, you could move the asteroid off its Earth impacting course if you had enough time. There's the impactor, which would be my favorite because it's so simple. And DART mission and the Deep Impact mission demonstrated the fact that we can run into these targets if need be. In a worst-case scenario, if you had a large object and little time, you could use a nuclear explosion. Much like the Armageddon movie in '98. We'd have to bring back Bruce Willis. But the 3 most important things for mitigating a potential Earth impact are to find them early, and find them early before they find us.
And a recent example of that need occurred in 2013. It was a year when it was known that an asteroid named 2012 DA14 would be passing extremely close to Earth.
A very close approach. And it was going to come within the ring of geosynchronous satellites. So that's really close. It's almost scary close in the sense that you want to see whether it's going to hit any satellites. But we knew that it would not hit. And we had been tracking this for about a year and predicting this close approach. So it was an event. And we had a NASA TV show hosted here at JPL in which we were planning to talk all about the close approach. There's nothing to worry about, gonna come really close, and these things are rare, but we know that it's not gonna hit.
Now, DA14 is not a threat. It will not hit the Earth. Scientists say the closest it will get...
Well, the night before that, what should happen, but on YouTube, all these reports of a massive fireball in Russia, in the city of Chelyabinsk. A lot of the videos were from dash cams. And they showed a really massive fireball coming in that was clearly much brighter than the sun. So that's a major event. It became evident that our little story of an asteroid coming really close to the satellites was being totally preempted.
Well, right now I am joined by Paul Chodas. And Paul, we probably have to address right off the top this meteor that hit Russia overnight.
What an exciting day. We feel like it's like in a shooting gallery here. We have 2 rare events of near-Earth objects approaching the Earth on the same day.
What can you tell us about this? Anything at this point?
First of all, the 2 events are unrelated. The meteor over Siberia and over Russia was not related to the asteroid 2012 DA, and they're not in the same trajectory, the same orbit. It's simply a coincidence that they happen to hit and come near the Earth at the same day.
How big was this meteor?
The meteor, we think, was around 15 meters in size, which is about 1/3 the size of DA-14 itself.
Okay, so it's much smaller.
Much smaller, and you can see what sort of destruction and shock wave that a smaller asteroid can produce. It's like Mother Nature is showing us what a small one, a tiny one, really can do.
The energy released is estimated to have been equal to a TNT blast of 500 kilotons. Many times larger than that of the atomic bombs used in World War II. The shock wave blew out windows, damaged buildings, and caused upwards to 1,500 injuries, including reports of skin burns and temporary blindness. A question raised was, why wasn't this asteroid detected? The answer was that it had approached the Earth from the direction of the Sun. Looking towards the Sun is a blind spot, not only for our eyes, but for telescopes too. To have had an advanced warning of the Chelyabinsk meteor would have required spotting it in a darker part of the sky. The last time an event like Chelyabinsk occurred was more than a century ago. But the fact that such a small object, believed to have been no larger than 50 feet in size, can cause such damage is yet another warning issued by Mother Nature. For there are likely millions more near-Earth objects of this same size yet to be found. So how should the world prepare for the possibility of a major impact by a near-Earth object? In the United States, various government agencies annually take part in tabletop exercises in which they must react to a fictional near-Earth object impact. The realistic schemes are devised by JPL's Center for Near-Earth Object Studies. The mastermind for creating these fictional threats of doom is the center's mild-mannered Paul Chodas.
The conference is called Planetary Defense Conference. They have been going for 15 years now, more, almost 20 years. At each of these, we have typically have exercises where we kind of ask ourselves, what would happen if? And at many of these, I put together scenarios of an impacting asteroid heading for the Earth, and simulating that and calculating what we would know when.
One exercise, played out in 2021, began with a new asteroid of an undetermined size being discovered by a ground-based telescope. It is some 35 million miles away, about a third of the average distance to the Sun. The discovery is relayed to the Minor Planet Center in Cambridge, Massachusetts, which collects and catalogs small solar system objects. News of the asteroid is then passed on to JPL.
Paul Chodas. And we pick that data up. We do that routinely. All of this is automated, so we would compute its orbit as accurately as possible, and the uncertainties in that orbit, which initially would be huge, and determine whether or not there's any chance of impact. Now, for this particular scenario, that impact is only 6 months away. And so our software would immediately detect the fact that this could hit the Earth. We need more observations.
As it goes past. So it's pretty cool. Oh, we have a lunar eclipse.
A mere 6-month lead time is dire news. But initial calculations show that the probability of an impact is low, about 1 chance in 2,500. But to have any confidence in this estimate, more observations are needed.
And so, depending on where the true impact trajectory is,
for a week, astronomers across the world aimed their telescopes at the night sky. And with each observation, the odds of an impact increased.
What is it, 400-day arc now?
Continuing to track it gives us better and better idea of whether or not it might impact. But there's the other matter of knowing, well, what are the effects of that impact? And that depends on the mass of the asteroid, which is basically its size. But we never really know its size accurately unless we have something like radar on it, or we visit it with a spacecraft and take images of it.
These two options aren't feasible. Radar is only effective when an asteroid is near the Earth. By then it will be too late. And with the impact just 6 months away, there's not enough time to launch a spacecraft to make up-close observations. So virtually nothing will be known about the asteroid's size and the damage it might cause.
The risk corridor. Let me move ahead to through a lot of this stuff to.
By the end of the first week, the probability of the asteroid hitting the Earth has climbed to 5%, or 1 chance in 20. As to where the impact may occur, the potential areas are at first literally all over the map, covering 2/3 of the Earth's surface.
Large swaths of the Earth are at risk initially, and it's our job to get a better and better orbit to narrow that down so that we know where the asteroid is headed and we can isolate the region of the Earth where it might hit.
To make matters worse, for the next few days, new observations by ground telescopes aren't possible due to the glare of a full moon. Astronomers use this time to search through their archives, looking for any possible past signs of the asteroid buried in their records. Meanwhile, for policymakers, a major question is what information should be shared with the public and when.
The data on which we base our orbit calculations are really international in scope, and they're available to all around the world. And the other orbit computers can run their calculations, maybe not quite as elaborate as ours, but come up with similar results. So it would be very difficult to kind of sit on this impact prediction and not tell anyone.
The group's suggested headline doesn't mince words. Newly discovered asteroid poses risk of Earth impact in 6 months.
These are just nominals.
Another week goes by. The effort to comb through past data has paid off. It shows that the asteroid had passed by unnoticed 7 years before. With this orbit data in hand, a better prediction of the asteroid's flight path can be constructed. The news is not good. The impact probability is now 100%. The potential target areas are narrowing too. A new headline is prepared. New observations confirm asteroid will impact in 6 months. The regions at risk are Europe and North Africa.
In this particular scenario, with only a few months of warning, it's really impractical to think that we could deflect this particular object. So then this scenario was designed more or less to deal with the civil defense issues of what you would do to evacuate areas once you knew more or less where it's hitting and once you knew more or less its size.
If the asteroid is as large as 160 feet, the impact is expected to be as powerful as the atomic bombs used in World War II. If it is 1,000 feet in diameter, destruction would be measured on a continental scale. A half-mile wide asteroid could mean global catastrophe. Meanwhile, an international effort has been exploring how a space mission might protect the Earth.
We did talk about, what we could do to mitigate and whether there would be any possibility. But with 6 months, there's not much.
It's soon apparent there's not enough time to attempt a deflection technique that might knock the asteroid off course. The only option left is to try to launch a spacecraft armed with a nuclear explosive device.
We have engine ignition.
And because so little is known about the asteroid, The recommendation is to send as large a bomb as possible, and then hope for the best. Of course, this assumes that a spacecraft capable of being quickly armed with a nuclear device is possible. Currently, no such rapid response capability is known to exist. Meanwhile, observations by the infrared space telescope CNEOS provide the first information about the asteroid's size. It is likely no more than 500 feet in diameter, and the impact zone has narrowed down to a region mostly within Germany, Czechia, and Austria. Among the cities at risk are Munich, Prague, and Vienna. It is now 6 days until impact. The asteroid is 4 million miles away and now in range of JPL's radar imaging assets. The size of the asteroid is further refined. It is somewhere between 300 and 400 feet in diameter. Estimates of how powerful the impact could be range from 9 to over 150 megatons. To give those numbers meaning, a single megaton contains the energy equivalent of 1 million tons of TNT. The day of impact arrives. The asteroid enters the atmosphere at the precise time predicted. The world can only await what will follow. Today we know of more than 1 million asteroids in our solar system, and thousands are found every year. Most reside in the asteroid belt between Mars and Jupiter, and they pose no threat from that location. Of concern are asteroids that are nearer, especially those that can cross Earth's orbit. It's believed that 90% of the near-Earth objects that could cause a global catastrophe have been found. But there are estimated to be thousands of asteroids large enough to cause severe damage over a wide region that have yet to be discovered. But that knowledge doesn't seem to keep asteroid hunters awake at night.
These events are so very unlikely to happen that it's not something that we lose sleep over. In fact, I feel more confident in the sense that we have capability to deal with them.
Out of the tabletop exercise, there was one big takeaway: greater awareness of the extreme challenges that come with a late discovery.
The bottom line of that exercise is that that asteroid could have been found earlier, at least 7 years earlier, with a better asteroid survey, a more sensitive survey, such as CNEOS surveyor.
Had a more robust detection system been in place that included a space infrared telescope, this fictional asteroid might have been known years earlier, allowing for a number of mitigation options. There could have been time to build and launch a reconnaissance spacecraft to determine the asteroid's composition, mass, and size. With that knowledge, a plan of action to divert the asteroid could have been devised. So what is the best line of defense? The answer is worth repeating.
The primary goal for defending against near-Earth objects that are on Earth impacting trajectory is to find them early, and find them early before they find us.